go ahead and jump in. We have an hour. Hopefully, it won't take us the whole hour, but we're going to do 5.6, calculating centers of mass and moments of inertia. It's a little bit shorter than the last section was. So, and honestly, I'm just going to kind of fly through the notes parts and just worry about the examples. And you guys can always rewatch stuff or read the PDFs. Granted, I have to get it on the modules for you. Apologies for not having done that. I really have been super sick, and I'm not normally someone who kind of complains about that kind of stuff, but yeah, just not used to it. Yes. I probably haven't been sick in like a significant amount of time because of as much as I don't like some of the things in Florida, you don't really get sick that much. Not that I would admit that to certain people, but obviously it's true. Okay, so here's what we're doing. This is a sketch of region R, and it's always helpful when you show a figure. So if you're reading over something and you're like, oh man, I kind of wish I knew what this looks like, draw it out. Okay, so using the expression developed for the mass, we see that M, sorry, that's only one. I'm so used to us doing 2 or 3, dm, so 0 to 3, 0 to 3 minus x, x, y, dy, dx. 0 to 3, x, pi over 2, 1/2 x, 3 minus x squared dx. That's going to be 9 over 4 x squared on top minus x cubed plus x to the 4th over 8. And then we have to go from 0 to 3. And if we do all that, we get 27 over 8. So the computation is straightforward, giving us a mass of 27 over 8 kilograms. You're going to want to make sure that you're paying attention to your units in this section. Sorry, my this is being so stupid. Okay, finally. Not moving that much, but at least it was letting me go up and down. Whatever. All right, next. All right, we have a nice little my, mx, and my. All right, finally. Okay. Let's get this rocking. All right, so considering the same triangular lamina R with the following vertices. I guess that would have helped me if I read it last time. And with the density, find the moments M sub X and M sub Y. So M sub X uh, 0 to 3, 0 to 3 minus X, X, Y squared, dy dx. You go through and you work all that out, guys, and you're going to get 81 over 20. You can feel free to do that. It'll be a good self-check for you. Okay. All right. Okay. Don't like that this is not visible. So, all right. So we are going to find the center of mass, again, considering the same situation we've been dealing with. Find the center of mass. So center of mass, you can see there, we're going to do X sub C and Y sub C, which is going to be, basically, we're going to do sub C equals moment M divided by the mass. So all right, so notice that the center of mass is 6/5, 6/5. Is not exactly the same as the centroid, which is 1, 1 of the triangular region. This is due to the variable density of R. If the density is consistent, then we just use constant, not consistent, sorry. Okay. This value cancels out from the formula, so the constant density, the center of mass, coincides with the centroid of the lamina. Sorry. All right. Okay. We are moving and grooving. Okay, finding mass moments and center of mass. Find the mass moments and center of mass for the lamina of density being rho xy equal to x plus y occupying the region R under the curve y equals x squared. and the interval is 0 to 2. Look at the following figure. So we have to do a decent amount of work, but hopefully we can squeeze it all on this slide. If not, we have a little wiggle room. So we have our mass. Yeah, we'll probably definitely need another slide. Oh, you guys should know me by now. I'm writing this big. So we're going to end up with m equal to 36 over 5. So that's the first part of it. So then we also need to compute the moments, which I think I'm just going to do on a new slide. And then hopefully that'll be like it for the extra slide. So we'll have m sub x Okay. So then okay. So that is those two parts. And now we're going to use those to find the center of mass. I'm not going to rewrite the parts because you guys should know them. Not the parts, I guess the formulas. You guys can get them from the other slide. That's that one. Okay, so the center of mass would technically be okay. Right. All right, so to compute the centroid, we assume that the density function is constant and hence that it cancels out. Okay, so we have to find the I'm gonna find x sub c and y sub c, and that's all we basically have to find, but then we put it as a point. So I'm gonna try and put the formulas further over so that we can have more room. Okay, so hopefully you guys can get the formulas. I'm just gonna go ahead and go straight into them, try and get them to be all fit on here. Oh, that's E. That's an E. Sorry, guys. So that's going to end up being 2e cubed over e cubed minus e, which is then just going to be 2e squared over e squared minus 1. Okay, that's the 1 point or 1 part. Hopefully we can get this other one in. So y sub c is going to be 1 to 3, 0 e to the x, y dy dx over 1 to 3, 0 to e to the x, dy dx, and it's 1 to 3, e to the 2x over 2 dx over 1 to 3, e to the x dx. So that's gonna take us over here. 1/4 e squared e to the 4th minus 1 over e squared minus 1. It's going to bring us to 1/4 e squared plus 1. Okay, so that's the second part. So you put those two together and you have the centroid of the region, meaning together as in a point. So the centroid is 2e squared over e squared minus 1, comma, 1/4 e squared plus 1. Okay, so the most correct answer. Right? So you now have your moments of inertia. Okay, so we're going to solve some problems. Concept now. I'm gonna give you a few minutes because I'm fixing my slide numbers. No longer match. We're gonna be on 11. Okay. So using the expressions established, find the moments of inertia. So we would have I sub x equal to y squared p xy dA. And so 0 to 2, 0 to x y cubed, dy dx. And that's going to be 8/3 have I sub y x squared p of xy dA 0 to 2, 0 to x cubed y dy dx. That's going to be 16/3. And then I sub o over the region. So that's 0 to 2 and then 0 to x. X squared plus y squared. And that gives us okay. Righty. If we compute the mass of this region, we find that m equals 2. We found that the moments of inertia back in example 5.58, so moments of inertia found in example 5.58. So from these data, the radii of gyration with respect to x, y, and z, or x and y in the origin, are respectively okay. Right. So take a minute with this definition. Take down as much of it as you can. You can obviously tell we're going to be dealing with them. What just happened? Okay. Let's move on to the next slide. Yeah. Not what I wanted to do. All right. So here's what's going on. We suppose that Q is a solid region bounded by x plus 2y plus 3z equals 6 in the coordinate planes and has a density of x squared y z. Find the total mass. So the region Q is a tetrahedron. Tetrahedron. No, yeah, that's what that is. Meeting the axes at the points, and you can see them. To find the limits of the integration, we're going to let z equal 0 in the slanted plane. So then that will give us z equal to 1/3 6 minus x minus 2y. Then for x and y, to find the projection of q onto xy plane, which is bounded by the axes and the line. So the mass is and this is why we had to do triple integration first. So we're going to go from 0 to 6 to 0 to 1/2 6 minus x and 0 to 1/3 6 minus x minus 2y. X squared yz dx dy dz. You do all that, you end up with 108 over 35, which is approximately okay. All right, we're almost done. We'll be getting out a few minutes early, I think. All right, so we have used this tetrahedron before. It's the one you just saw. And know the limits of integration, so we can proceed to the computations right away. First, we need to find the moments about the XY plane, the XZ plane, and the YZ plane. So we're gonna find some moments first. We may need an extra slide, I'm not sure. So that's gonna be 54 over 35, which they give us the decimal, so we might as well include it. 1.543. And we need the moment XZ. Oops, guys, I dropped this each time, sorry. It's, but you guys probably caught that, so hopefully. Or it might have ended up being somebody's question. So. All right, so we do need another slide. We need to figure out the center of masses now. So, or the center of mass using certain things. So, X bar so 243 over 35 divided by 108 over 35 is going to be 243 over 108, which is 2.25. Y bar is 81 over 35, 108 over 35, which is just 81 over 108, which is 0.75. And then we have V bar, which is 54 over 35 over 108 over 35, which is 54 over 108, which is 0.5. So if we put all of that together, you get the center of mass for the tetrahedron Q is 2.25, comma, 0.75, comma, 0.5. Oh, all right. So last problem. I have a short announcement to make after, so no one else can leave that video. All right, so once again, we can almost immediately write the limits of the integration, and hence we can quickly proceed to evaluating the moments of inertia using the formula stated before, the moments of inertia. So we have I sub x you guys should be able to figure out the formula, so I'm just going straight into it. So it's going to be over Q we may need another side, not sure. 0 to 6 0 to 1/2 6 minus x, and then 0 to 1/3 6 minus x minus 2y. And then y squared plus z squared x squared y z dz dy dx will give you 117 over 35. I'm not caring about the decimals right now. It's 3.343 if you want it. I'll just put it there, 3.343. Right? So now we're going to do I sub y. I'm just going to go straight into the problem. So that's 684 over 35, which is 19.543. And then IZ is going to have the same setup. All right, so that's it. Those are our answers. That's all they wanted there. Didn't have to turn them in the points, didn't have to do anything extra. That is it. 1 savings.